meeting of research network people to tell you of some of the plans in astronomy, not just radio astronomy, for using the research networks and the grid infrastructure. And I will illustrate that with a few examples of the things that we're interested in. And I think you'll see at the end that we expect to be very heavy users of the research network infrastructure, and in particular, I don't think that people who are providing hundreds of gigabits per second of capacity should worry that there won't be people to use it, because we have our eyes on that capacity. 4 types of use of the research networks are envisaged. First of all, the transport of raw data from the telescope or telescopes, as I'll point out in arrays of telescopes, to the data processing facility or database. And once that's there in the database or the processing facility and has been analyzed, then distribution of that data to the users, the actual users who propose the observations, that gets distributed soon after it's been produced. And there's a proprietary period usually for astronomers of a year or 18 months before it goes into the public domain, into the databases when anybody can use it. So the third thing then is the mining of databases for when the data has come out of the proprietary period, and those databases can be located anywhere in the world and cover the whole span of astronomy from the radio wavelengths up to the gamma rays at the very shortest wavelengths. And the final final area where one could envisage use of the networks is in real-time remote control of the telescopes. If we look at the transport of raw data, the required capacity that we're talking about is really driven by the radio telescope arrays. And these arrays create images of the radio sources anywhere in the universe by a technique called interferometry. And that's the I in the VLBI, which stands for Very Long Baseline Interferometry. And in these interferometers or arrays, we have networks of radio telescopes which are spread over hundreds or thousands of kilometers, which actually provide a zoom lens for us astronomers. And in fact, it's not actually, the location of radio telescopes is not restricted to the surface of the Earth. We actually have a radio telescope in orbit around the Earth at the moment, which gives us separations or baselines of lengths up to 30,000 kilometers. This gives us the most detailed pictures of distant stars and galaxies that we have in any branch of astronomy. And the sort of detail that we can get is equivalent to being able to see a golf ball on the moon. And of course that gives us a good resolution on the moon, but at the distance of the center of our galaxy, it means that we can see objects which are about the size of our solar system. Now, this technique requires that the transport of data to the central data processing center is almost simultaneous in order for us to do our interferometry. Now, let me show you a few examples of these types of radio telescope arrays. Start off with a couple of national examples. This one is called eMerlin for electronic Merlin. The Merlin is multi-element radio link interferometer, and they're changing the radio link into fiber link. And the idea, the plan, and the funding is almost there to start the project, is to connect 6 telescopes which are spread over about 250 kilometers in the UK to the Jodrell Bank Observatory near Manchester. And the sustained data rates per telescope that are expected are 30 gigabits per second. And the requirement for these large bit rates is to get sensitivity to very faint radio sources. And this telescope is expected to be operational in 2006. Now, another national example, or almost national, is in the Netherlands. This is a telescope called LOFAR, which stands for Low Frequency Array. And here, the telescope is the stations of the telescopes, or the elements of the interferometer are spread over a distance of about 300 kilometers in a log spiral fashion, as you can see on this diagram. And the data rates coming out of this telescope are quite phenomenal in the sense that at least the planned data rates, they aren't there yet, that the total data rate into the center could be as much as 20 terabits per second. Now this is to allow for you need a large data rate to get sensitivity again, but you also need to, in this particular case, to have quite a number of bits per sample in order to remove the effects of radio frequency interference. The area in which this telescope would work would be in the short wave to the FM bands, and there's a tremendous amount of interference that can be expected from man-made causes. Find my pointer again. Where is it? Which key? Oh yeah, thank you. It'll teach me to have a white background. Okay, just before I go on to the next slide on this particular set, let me show you what sort of thing we expect to do with this zoom lens. This is a picture, an optical picture of the so-called Hubble Deep Field. It was taken in optical wavelengths by the Hubble Space Telescope. And this small area of sky, you can see 2,500 galaxies. All these fuzzy dots here are galaxies, all containing 100 million stars or so. Now, if we just concentrate on one of these little galaxies and observe it in the radio domain, what you can see is what is a typical radio source, which has a little spot in the middle, which is coincident with the center of the galaxy, and a couple of jets which point out, which go out on either side, out to sometimes as far as 12 million light years. Now, this is what we're interested in studying, and this sort of thing you can study with interferometers which are a few hundred kilometers across. But if we concentrate on the center with one of these longer baseline arrays with telescopes which are thousands of kilometers apart, then you see another structure which is aligned with the previous structure, and we know from other information that probably this little red spot in the middle here is where the black hole that's at the center of this galaxy is located. So this is what we're interested in seeing. Let me go back to this picture again. And show you a European scale interferometer. And this is the European VLBI network. And what's shown here are of the order of 12 telescopes, all indicated by those dots. And with, at the moment, a hypothetical link via fibers between those telescopes and the Central Data Processing Center in the Netherlands at the Joint Institute for VLBI in Europe, which is my institute. Now, the sort of thing that we're interested in transporting here is data rates of the order of between 1 and 8 gigabits per second per telescope. So what will come in to the Netherlands would be data rates between 32 and 256 gigabits per second, depending on the bandwidth per telescope and the number of telescopes which take part in the observations. Now, you can see that I've got various arrows indicating links to China, to South Africa, and to the United States. In fact, these arrays of telescopes are global. And I'll get to that in just a moment. But first, let me show you a couple of pictures of radio telescopes, just to show you what beautiful things they are, if you like these things. This is a radio telescopes in Sweden. This nearest one's a 25-meter telescope, and in the golf ball at the back there's another 20-meter telescope that works at high frequencies. And then one in Germany, which is the 100-meter telescope, located near Bonn. This is something that's worth a visit if you ever get near the place. To see a 100-meter telescope moving around is quite a spectacular sight. Now, each of these telescopes in our network is a nationally funded telescope, and the participation takes place via a consortium which we've set up almost 20 years ago to do this sort of work. And the way that the observations are analyzed at the moment is by recording each of our signals, the signals that come in at each radio telescope, on a tape and bringing it to a central place. This is in the basement of our institute. There are 16 tape drives which play back this data, and got a schematic diagram here of how this works. We record that data at rates up to a gigabit per second, and we transport that via airplane to Holland. And the data rate which is recorded is of the order of 300 terabytes a day. Now, luckily, we don't have to store that. We run it into our special purpose supercomputer, which just does a multiply and add. That's something like 10 to the 14 operations a second. And out the end, you can see on the left-hand side down here, we get astronomical data at around about a gigabit per second at the maximum if we are able to actually transport that. Now, I mentioned that we have connections globally. Let me show you the global picture of all the telescopes that take part in these sorts of observations. And there are something like 45 telescopes on that picture. Not all of them can see the same point in the sky at the same time because of the curvature of the Earth. So we typically run at the moment up to about 20 stations, 20 telescopes in an observation. And if we take a look at the United States, there are something like 10 or 12 telescopes there that take part in these observations. We're very interested in having them join in a fiber-linked network, and there's already some funding there to do a pilot experiment of their own inside of the United States between the Haystack Observatory, which you can see on the top left, same place as Millstone, the Millstone radars, and that will run the data down to MIT and then back up to the Haystack Observatory. And a second telescope somewhere near Washington will come send us data up via something called the BOSNet, which I know nothing about, but I'm sure some of you here do, up to the telescope. Now, what we're interested in doing is making all these connections global, as I say, and what I'll get to in just a moment is some of the plans we have in Europe. So if we describe this sort of network, the network we have, its characteristics are that it's a multi-point to point connection, so we're running all the data into a single point. It's asymmetric, and because certainly in Europe and across to the United States, these are different countries and different networks involved, it's a very heterogeneous system. Now, the final thing is another global scale telescope called the Square Kilometre Array. This is something which is not funded yet, but the discussions, the plans are already starting. There's a global collaboration. Might be operational in 2015. And the idea is to distribute perhaps 30 or 40 patches of collecting area across the globe to make up a total collecting area of 1 million square meters. This would, of course, give us enormous sensitivity, which is what we need. We're always looking close to the noise, and the the data rates that might be required there are also possibly up to terabits per second coming back into the center. So you can see that in the terms of data transport, we have very significant requirements. Now let me see if I can run through this fast. If I turn now to data mining in astronomy, in Europe we have a project which is being supported by the European Commission for accessing databases of the European Southern Observatory, and in particular the very large telescope that's located in Chile. And here shows a picture, not a photograph, but an artist's impression of 4 8-meter diameter optical telescopes, which are now in operation. And this database mining is already ongoing, and the interesting thing is to broaden this out into something called the Virtual Observatory, which is a project which has a lot of visibility also in the United States. These data sets are going to be of the order of hundreds of gigabytes to hundreds of terabytes in size and at multiple sites. And the database access that's needed will be several gigabits per second in order to access these things correctly. Now, there are other projects which require a lot of activity in this area of database mining. Here's a satellite which is called the Gaia, which is going to make what they call a high-precision census of more than 1 billion stars of the galaxy. And what this means is they will measure the positions and motions of 1 billion stars in our galaxy, and this is a major project which generates an enormous amount of data. And we go on to this next one. This shows the analysis concept that's required. The database will end up after 5 or more years of observing. It could be as much as 500 terabytes. And the way that the data analysis will be done will be in distributed computing. The total processing requirements that they're looking at is requiring something like 10 to the 19 flops. So this is again a fairly substantial effort and requires a lot of distributed computing power, which will obviously make use of the grid. Now, if we just turn to the EEVN, it's a real-time connected radio telescope as large as Europe. So I said, just to summarize that, we're looking at transporting raw data streams of 1 to 8 gigabits per second, and we do that via the national research networks and via JIVE. We're looking at real-time control of the observing process, and so on. And this will generate new astronomical capabilities for us. It'll give us a considerable improvement in operational reliability and flexibility. As you might imagine, these tape drives that we use, although they're state-of-the-art, they're the weakest link because they're mechanical, and it would be very nice to get away from them. The time scale that we're talking about for this activity is post-2005. Now, the impact that we would get from this in terms of science would be having a wide bandwidth that was always available. That gives us, as I say, a major increase in sensitivity. At the current time, the maximum bandwidth we get with the tapes means that we use up tapes at a very fast rate. It's something like 75 minutes a tape per station, and they're very expensive, so we don't have very many of them. So we don't do very many of these high bandwidth observations. So we're also, one of the things that we're interested in doing is looking at making movies of variable sources like exploding stars. And I've got an example of one here, which is a supernova. It's an exploding star that went off in a galaxy called M81, which is shown on the left. That's the optical galaxy, and this little round spot on the lower bit there shown is where the supernova went off. And on the right-hand side, the series of radio images that were made between 1993 and 2000 of how this supernova actually expanded and slowed down. I haven't got time to go into that, of course, in the details. As far as the operational impact is concerned, we can see the improved reliability, much more effective monitoring of our network, not of research networks, and flexible scheduling as being something that will be very, very interesting. Now, what we've done is to put in a proposal in the latest call for proposals from the European Union and the IST area for what we call a pilot project, and we plan to, we propose to link up 4 of our EVN telescopes and possibly 1 US telescope to the central processor, using as much off-the-shelf technology as we can. And we propose that we do this with bit rates up to 1 gigabit per second, and we need a latency of 1 second. Well, that means we that we need to have all the signals from all the telescopes arrive within 1 second. We have to buffer our signals anyway before we put them into the central processor, because the most important thing is to have simultaneous signals going in, so that we match the wave front that came from the radio source itself. So we have to take out the effects of the size of the Earth on the time that it takes for signal to arrive at one telescope and at the next telescope. So what we're planning is to set up this system, do network monitoring of the research network, see that this is possible to do, and assuming that it is, at the end of the project, to do some astronomical end-to-end testing for several periods of weeks at a time. And what we're talking about here again is sustained operation. I mean, in order for us to do our observations, we need to have of the order of 8 to 12 hours of data coming in, all at the same bit rate. The partners in this project are all the radio telescope institutes in Europe, 2 US observatories, Dante and NICEF, which is the Particle Physics Institute in Amsterdam in the Netherlands, who provide us with a link into the Datagrid project. Here's a diagram of some of the data flow from an individual telescope. Almost all of that, the hardware there exists. There's something on the second to right box called the SUE, the station unit. That needs to be a special purpose set of cards need to go into that. We need routers. We would we'd very much like to find a simple router. We don't need all the flexibility of switching on both sides of the router, but we'll have to see what the market provides for us there. Coming into the correlator site, data comes in off the backbone network into the POP, and then into down the line into our local router, and then into the correlator itself. This all we think is relatively straightforward, but there obviously are technology challenges here. Networking at multiple gigabits per second on the short term, as I've heard during this week, is not by no means a straightforward activity, especially when we have to do it via concatenated national, regional and pan-European networks. I've heard this week about using dedicated wavelengths. It sounds like a good idea to me, but to see whether that's possible. And of course the quality of service is something that we need to look into. We're not too concerned if we lose the odd packet here and there, but we have to know which packet has been lost. And I note here a technology challenge is still perhaps more a cost challenge. There's last mile connections to the sites. They're mostly all in remote areas, and so that needs to be overcome. And on the longer term, networking at terabits per second is certainly a technology challenge. So as a summary, astronomy is clearly going to be a heavy user of the research network infrastructure. The data mining, distribution and distributed computing are going to require rates of several gigabits per second, certainly comparable to applications in high energy physics, which we'll be hearing about shortly, biology and remote sensing. But it's in the raw data transport in radio astronomy and interferometry that's the novel application that goes well beyond these other requirements. It pushes the envelope for sustained data transferred at very high rates. And the challenges are this international connectivity at these very high data rates, quality of service, and the cost. Thank you very much.
Thank you, Richard, for this exciting presentation. Now we have time for a few questions.
Can you turn it on? It's not on.
Yeah, one of the issues that comes up quite regularly is that of data compression. In astronomy, have you looked at appropriate standards and quality metrics for data compression?
Well, for most of the radio telescope arrays that we use, it's not possible to compress the data. What we actually record at the moment, what we would transmit, is either 1 or 2 bits per sample. So there's no compression to be done. It turns out to be the most efficient way of doing it. In fact, it's always been a source of amazement to me that we can generate those pictures of radio sources that I showed you, but just by measuring whether a voltage has gone positive or negative in the sample time. That is the case.
Well, presumably you could use run length encoding, right?
Sorry?
You could use run length encoding.
I'm sorry, I'm not in this area. I don't even know what that is. but I tell you, there is in this telescope called the LOFAR, the low frequency array, there is provision for 14 bits per sample to try and take care of radio frequency interference. Now, I can imagine that there in that area one could employ compression if needed.
Another question? So then let's thank again Richard. So the next 2 presentations will cover European Union-funded grid projects. The first one will be presented by Dietmar Erwin. This is the EUROGRID project. Dietmar Erwin is the head of the Systems Operating Group at the Forschungszentrum in Jülich. He is also project leader of the UNICORE project. The UNICORE project will certainly be explained, and you know this is some kind of another middleware besides Globus.
Good morning. During this conference, 2 things occurred to me. One is, at many of the slides that I saw during various presentations, the term grid was there, practically taken as grid computing is there and is a fact. This was also true in Robert's presentation, where grid appeared once, and he described a perfect grid application. That was wonderful. The other thing that occurred to me is that people came to me during the breaks and said, well, you're talking about grid computing. What really is it? So what I'm going to try to do today is explain to you in a few words the vision of the grid, the challenges of grid computing, and give 2 examples where I think I'm competent to speak about. There are other examples. Following me will be the Datagrid Project, and there are other projects in this area. And finally, I would like to summarize and try to address the question, where is grid computing going? And I borrowed from the Greek, Latin origin of this area, quo vadis clatri. Grid computing was introduced in 1998 by a book from Ian Foster and Carl Kesselman, Grid Computing, the new challenge for high-performance distributed computing. And they had a very compelling analogy, namely comparing the computation of the future to what you see in power grids, in the electric grids. This actually would not have worked in Germany because the power grid, as it's called in the United States, is called the power supply network in German, so that would not translate easily. So their vision is, their analogy is, you have a power plant somewhere you have connecting lines somewhere, and all you need to do is press a button and the light goes on. That's that easy. Or to transform it into the world of computing, you pose a question, the system goes around and looks at the various computers in the world, finds one, computes, and eventually comes up with the answer. So this is the vision, this is how computing should be, this is the easy part of it, and this caught on immediately the attention of all the people who are not technically involved in this, politicians, funding agencies, to some extent the press. So this was the part that brought all the various research together under one umbrella of grid computing, and if you look at conference announcements in the last 2 years, you see many conferences with the label grid in their title. So another way of putting it is to say, well, grid computing, and I'm coming to what it is, should be as easy as finding something on the web. Now the difference between web and grid computing, as you will see on this and the next slide, and I thank Ian Foster for allowing me to use this foil, is that the web is uniform access to documents, HTML documents, whereas grid computing is a flexible, high-performance access to all significant resources. And we saw 3 examples in the last presentation, namely instruments, and I have instruments here, an electron ring or a PET. You could also have telescopes as instruments. You need computers, high-performance computers, data, archives, software catalog, software application, visualization, and the colleagues. So the grid computing, in a nutshell, is on-demand creation of powerful virtual computing systems. Taking this as being there today would be simply believing in the hype that is sometimes created. So what are the challenges of the grid? Well, there are several of them. Architecture and implementation, that is one of the challenges which workers, researchers, developers in grid computing are faced with. Security is certainly one of the challenges, especially if you come to commercial, industrial application where security is an extremely important issue. Applications that are enabled to run on the grid are a challenge. And finally, deploying and using grid technology is equally not as easy as one might think it is. And this all boils down to standards that have to be there to make grid computing successful. Let me go a little bit deeper into the challenges of the various components. The architecture, there are different approaches to grid computing, and they are essentially complementary. The horizontal approach or a vertical approach to grid computing, horizontal in the sense that you build a layer on which all other applications for the grid can use, or a vertical approach that you build a solution top-down from the interface down to the networking level. The architectural approaches can be described as toolkit-based approaches versus an integrated approach. And 2 examples of these different approaches can be found if you take the Globus approach, which is horizontal and toolkit-based, and the UNICORE approach, which was developed in Germany, is initially vertical and integrated. So the different projects, the different architectures explore different ideas and create novel solutions, and it is important at this stage where grid computing is not a given, settled idea, that different avenues are explored to find best solutions in the future. Challenge is security. Well, we sometimes in the research in the academic area, in the research areas, security is considered an obstacle. But as soon as you have collaborations with industry partners, security becomes the #1 issue. This includes, of course, the typical security aspects, authentication, authorization, and, of course, integrity. The grid security relies on X509 certificates, but, and now this was addressed during the last 2 days in the PKI working sessions, there are multiple CAs, there are different policies, and how to map these is still an unsolved question. We had a very interesting and very path-breaking description of the Federal Bridge CA in the United States. This is yet to happen globally, so this can be applied to grid computing. So the summary here is standards alone, that is X509 as a standard, is not enough. It's also how you use the standard, how you deploy the standard, and how you make the standards compatible in a sense. Applications, as I said, we had a perfectly valid grid application described. So this is an application that could use the grid. However, is this application, is the code that exists in a position yet to make use of the grid technology once it becomes there? The question is today, probably not. There are very few applications that make use of grid interfaces, grid infrastructure. For some applications, this is completely impossible at the moment because nobody has the access to the source of those applications, typically commercial applications, take Nastran or others, and approaches have to be found actually to get those applications to be integrated into the grid. The cost of development and migration is to be considered here, the incompatibility of underlying systems, and before companies make investments, they want those issues to be resolved. The approach with portals to the grid might be helpful. What is essential is that applications that demonstrate the capabilities of the grid become available soon, and there are a few examples that are being worked on. Cactus is one of them from a different field, and certainly the application that will become through the Datagrid project will also be applications that show and demonstrate the power of the grid. Deployment, this requires effort on part of the participating centers. The users on the workstation, they have to install some software, some application, and application service providers that want to offer their services on the grid have to invest initially. But there are also then opportunities for new business models, for new ways of selling resources to the customers. And finally, as I come back to the challenge of standards, the grid solutions, as we see them today, use open standards, X509, SSL, HTTPS, and so on. They also develop specific protocols and standards. One example comes from the UNICORE project, where we developed the abstract job object to describe in an abstract form the task that is being done to do high-performance computing. This is exploring different approaches to get the best solution. I might say the Global Grid Forum, and this is a pitch for the Global Grid Forum, works on grid standards, not in competition to the established standards organization, but drawing the expertise from this field together to eventually bring standards from the grid area into the standardization processes like the IETF. Now I'm going to take the 2 examples of grid projects that have been developed in Europe and briefly describe what section, what portion of the whole grid computing scenario that I described initially they are addressing. First, the UNICORE project, which is now in its second phase under the name of UNICORE Plus, is funded by the German Ministry for Education and Research under this grant, and this is the typical things that you have to do to comply to the funding regulations. And EUROGRID is funded in part by the EU under the following contract, and they will run till the end of the next or the year 2002. Now, UNICORE goals. UNICORE stands for Uniform Interface to Computing Resources. So the vision here was to develop a seamless, secure, intuitive software infrastructure to access high-performance computing resources, initially in Germany. This was an initiative brought not from the end users in that sense, but from the computer centers in Germany that said, we have substantial compute power, different architectures, we have users that are using different systems, and what can we do to make the life of our users easier when they move their applications or when they use one center today and another center tomorrow? And when new systems come in, how do we minimize the training effort for those users to make use of the latest systems that we are providing? So to put it differently, and by the way, this first UNICORE project was started before the term grid was coined as such. So many of the projects that are being done now under the label grid computing have started prior to grid computing, building on ideas in the area of distributed computing, client-server computing, meta-computing, whatever was the buzzword of the day that the proposal was written. So UNICORE creates a high-performance grid computing environment in Germany. It delivers consistent batch access to different remote systems, as I said. It is hiding the seams that are created by the different hardware architectures, the incompatible system software, and the historically grown computer center practices and conventions. It is basically impossible to impose on an existing organization new rules, even if they are better than the previous ones. UNICORE supports multi-site and multi-applications, support for multi-site and multi-site applications for one job. That is, you can run one job on one system and without changing the job, submit it to a different system. Or you can have jobs which are composed of components which require the cooperation of multiple sites, for example, combining a vector processor and a parallel system on the granularity of jobs. This will then satisfy the requirements of the user, namely to get the optimal system for their problem, and it also satisfies the requirements of the computing centers to have the optimal solution of their expensive resources, and it allows use of specialized hardware and use of remote data. UNICORE was started out to exploit existing and emerging technology, of course, communication via the internet, vector techniques, Javas, and security based on X509 certificates, which is a design decision that we had to take early on, and we were fortunate to pick the right decisions. Some of the things we did not progress as we expected to do. For example, the security based on X509 certificates, everybody's using that. But we expected 3 years ago that since the e-commerce would be based on certificates, everybody would be familiar with certificates and doing e-commerce on that. But e-commerce did not move fast enough in this area. So we're still struggling with the deployment of the certificate infrastructure. And of course, we need minimal intrusion into the centers. That is, we cannot require the centers to change, for example, their existing batch systems. We have to interface with all of them. We cannot have the centers redo their internal naming structures, and we have to accept their local security measures like firewalls or DCEs. This is a look at the UNICORE partners. The map of Germany is sort of hidden in the background. There are the major supercomputer centers in Germany doing this, and we have a partner, Pallas, in Brühl, who is the software developer and doing the integration of the system in order to have this not stop as a research project and throw it in the wastebasket at the end of the project. They have a commercial interest to provide a commercially supported product at the end of the project lifetime. I think I can skip the UNICORE functions. I went through them already. We are having automated control of job flows. That is, we support automated computational experiments on different computers, secure access to remote data, and of course we want to we don't want to force the users to invent everything from scratch. So reuse of existing jobs is a must in UNICORE. A brief architectural picture, and you could start talking about another half hour on this one. It's a three-tier architecture where the user workstation has the client software, secure communication to UNICORE service as a different site. This is one site, this is a different site, is being done using certificates, securing this communication, and then an interface to the existing batch systems, one or more at a site. And if user has a job submitted to UNICORE that requires the services of another site, so the system here automatically does the necessary control and data and job transfer to do the execution and returns the results via this way back to the user. Briefly to EUROGRID. UNICORE as a German project would have had a rather narrow market and too narrow view, so we decided early on to have additional European partners there. And when the EU had its first call in 1999 with software related to grid computing, we've submitted a proposal under the acronym of EUROGRID, with a vision to build a European grid infrastructure that gives the users the same quality of access, seamless, secure access to high-performance computing resources in Europe and advanced computational science, or what is now called e-science in Europe. The EUROGRID partners, you see them here on this map, they are in various countries, and I come to them in greater detail in a minute. What EUROGRID wants to accomplish is strengthen the applications that can make use of the grid. We have applications from the biosciences, from meteorology, from computer engineering and general purpose grid services from the HPC centers. And in the EUROGRID project, we are going to extend the scope of functions that are provided by UNICORE, namely those that have been explicitly excluded from the UNICORE project, like interactive access, computational steering, and so on. And of course, we have the same dissemination and exploitation plan for EUROGRID. The BioGrid is to operate a grid for biomolecular simulations, where eventually either new code that is developed by researchers is made grid aware, or existing packages are made to understand, to make use of the functions of the grid by providing wrappers to translate the application-specific interfaces to grid interfaces. MeteoGrid builds on the German Weather Service's global weather prediction model as a central service, and will allow local weather forecasts, local weather predictions as application service providing solutions, making use of the central data that is computed for Europe and the world, and allow then low-cost weather predictions for certain regions. The computer-aided engineering grid will have a couple of simulations, in this example structural and electromagnetics, in the development of the new aircraft, the A380 actually should be, A380 from in Europe from EADS, And the goal is to have an internal high-performance computer for the engineers in this company to do their simulations, not restricted to one location, but using grid technology to harness all the locations. And finally, our partner Davis wants to provide a high-performance computing portal to the Daimler Chrysler and their partners, and they are also addressing the aspect of cost of computing, billing, cost estimates, because the engineer there always have the approach, where can I get my computation done either the cheapest or the fastest. In summary, UNICORE and EUROGRID, from the issues that I laid out initially, addresses architecture and implementation in a certain way. It addresses security. It addresses selected application. It does not address the whole scope of potential and possible application. And it addresses the issue of deployment and use, both in Germany and in Europe. And we're also working on standards together with the Global Grid Forum, and here we have a new project proposal with the EU in the latest call to explicitly work on standards and bringing the European expertise to the table, to something which is, we have to face the fact, is at the moment mostly US dominated and US driven. So where is grid computing going? Well, to realize the vision of grid computing requires that computer scientists, developers, and users work together. We started something from the point of view of computing centers to make offerings to the users. The bridge to the users is not that easy, because some of the users simply say, well, I have my SSH connection to a computer, and that's all I need. However, who has ever built a bridge across a river based on the count of people that swam across the river at this particular place? So we have to do some advanced investments to make for the future. Well, this is in progress. We have to have collaboration between the different projects. This is underway, so we do this, and this is ongoing. And one of the most difficult issues is we have to manage expectations. Grid computing will be there, hopefully. It is not there today, as sometimes depicted. This is actually the most difficult aspect, and I sometimes wonder what is worse, whether the airline magazines detected some topic and say this is the reality today, or whether politicians find some topic and say we have to have it today or yesterday. If we manage altogether coping with these issues, well, eventually grid computing will see the light, and there are questions, and I'm prepared to answer questions either now or later on. Thank you very much.
Thank you, Erwin, for this interesting presentation. Now we have time for a few questions. The floor is open. Can you invite the microphone, please?
Can you comment on the essential difference between the scope and aims of DCE versus grid?
DCE is one technology which addresses two aspects, namely security and a consistent data pace, whereas grid computing goes beyond this. DCE would be one potential technology which could be used to address those two aspects within the grid computing framework. We looked at DCE as one potential solution on which to build it, and we said we are not going to rely on DCE, because this would require DCE to be deployed to all the ones that would want to make use. What our approach was is we have to interface to the installation organizations, to sites, to computing systems that use DCE and make DCE data available as a data resource and interface the X509-based security to DCE-based security.
Other questions?
Since now eGrid and the Grid Forum of the US did merge together, will there be also a merging of the technologies, meaning Globus and UNICORE?
I wouldn't. This is a question of gazing into the crystal ball. The point is, we are having a project together. That it means Jülich, the research center in Jülich and Argonne National Lab, have a small project going on this year to be completed by November in time for the SC2001, demonstrating the feasibility of using UNICORE as a front end to a Globus service. This is sort of ad hoc demonstrate proof of concept. What we are aiming for is actually to have, when this is successful, which I believe it will be, to have a EU project together with Globus people to work on the best of breed from the two projects and to complement each other. Whether this either will be funded, I cannot know. But I'm sure that to be successful, the various projects have to come to use common standards, and UNICORE technology is built in such a way that the components can be exchanged by other components. So this is just then work, not a principal problem.
Another question? So then let's thank again Erwin. So our next presentation will cover the Datagrid project, the other presently EU-funded project. The presentation will be made by Olivier Martin. He was so kind to replace Les Robertson, who could not come. Olivier is working at CERN he is responsible for wide area networking, and I think in this audience Olivier is well known, so he will not need any further introduction. Olivier, please.
Because you gave a very good introduction to GRID, so I can go. Okay, so I'm substituting Les Robertson. The GRID is expected the GRID technology to be enable worldwide scientific collaboration, and I'm going to describe one example, well-known actually, example of worldwide collaboration, which is the high-energy physics, and more specifically the LHC project at CERN, and how we plan to use GRID technology in that context. Okay, so the project evolved. At the time we were searching for practical solution to the computing requirements of the next generation accelerator, the LHC, and at the same time the appearance of Foster and Kesselman's book on the GRID. So what are our problems? We have enormous quantities of data which will be generated by the LHC accelerator starting in 2005, 2006. Enormous, meaning several petabytes of data per year, which have to be somehow distributed worldwide. So in the previous accelerator, the way data was distributed was mostly by tapes, sending tapes. Now the volume of data in these next generations experiments are so large and also the network technology is now becoming mature to distribute everything by the network and do distributed computing not only at CERN on very large PC clusters but also worldwide. Okay, and of course vast quantity of data means enormous computing requirements. Okay, so these are, briefly speaking, we will have 4 experiments called Atlas, CMS, Alice, LHCb. The recording rates, the amount of data which will be collected at the computer center online is of the order of 10 gigabits per second. And as already said, we will accumulate tens of petabytes of data per year. And in terms of processing, it will require 200,000 of today's fastest PC, the 1 gigahertz type PCs. Okay, that's how this computing fabric will look with again thousands of PCs. We traditionally at CERN we have two levels of storage, disk and tape. Today we use tapes as to keep active data, and the disks are used as a cache. In future, we hope that the tapes will only be used for archiving, as that most of the active data can be kept on disk. Okay. Okay. That's figure is showing two things actually. It's a simulated event on one of these new detectors. That's another aspect of the high energy particle physics, is that we are collecting real events from the detector, but to prepare for that there is several years before, knowing the characteristics of these detectors, they are simulating a large number of events, and then they during the analysis of the events they compare the simulated data with the real data. The characteristics of the LHC is that you have very complex collisions with signals to noise ratio which is extremely low, which in some cases is equivalent to identifying one person in out of the whole world population. Okay, in terms of computing capacity, on this plot you can see where we were last year in January 2000 in terms of spec-int 95 and the expected growth from the start of the LHC and for the next 10 years. In the middle you see two curves. We try to plot what we can expect technology will deliver to us if the Moore's law continue to be valid. So that shows what we could expect at a constant level of investment. Unfortunately, the LHC needs in terms of computing by far exceed this what we could expect from the Moore's law. So there is a big problem with the funding, which partly explain why actually this with computing can be interesting. So that's the final slide showing various, you don't see it, but on the top left you see actually the data weights out of the detectors, which are at the range of 1 terabit per second in equivalent digitized data. This is of course impossible to record, so it is reduced, and what comes to the computer center is of the order of 1 to 10 gigabits per experiment. Okay. Now this is then some process which is done at CERN called the event reconstruction, which results into another reduction of the volume of data, and that's this data which has to be shared worldwide. Okay. So the reduction is about 1 to 10. Okay, and finally that shows the where the CERN the users of the CERN laboratory are located. So there are in Europe about 300 institutes, almost 5,000 users, and elsewhere, meaning North America, also South America, and in the Far East we have Pakistan, India, Japan also, China. There are a sizable number of institutes and users. Okay, so far we already mentioned we have a long experience in HEP with managing large clusters with processors of various kind. We started with Unix processors 10 years ago. We now most exclusively use standard PCs, dual processor PCs, Pentium 4, using Linux Red Hat, and huge disk farm mass storage. I already mentioned we have 2 levels of storage, and we so far succeeded in providing fairly reliable services and to accommodate the growth inside the CERN Computer Center. Okay, everything is commoditized. This now have become standard PC IDE disk. Ethernet are cheap, 10 megabit, 100 megabit Ethernet connections. And the only thing which is not commoditized are these expensive tape robots. Okay, so now the problem we have been faced with is to scale the existing methods by factor of 1,000 or more in 5 years' time. And while maintaining reliability, availability, and of course one of the issues with large PC farms is management operation is quite manpower intensive. Also has implication on the network infrastructure if you have a large number of PCs connected to gigabit speeds, and you need very high speed switches which do not really exist. You also need more down to the earth. If you want to have large number of PCs which are globally accessible, you need large number of IP addresses, which is not obvious given the number of elements we are speaking of. So, I mean, everything when you scale by this amount brings its own set of problems. So we have to find new levels of management and automation, especially installation, monitoring, diagnosing, self-healing. Okay, so it's actually out of question to provide all these requirements at a single site for a number of reasons. There are many, arguments, mostly political but also financial, against building very large facilities. As you know, CERN is a European international organization funded by most of countries in Western Europe, and each country has its own national constraints. They don't like to fund very large computing facilities in foreign countries. And also all these CERN member states, they have their own large computer centers which they would like to extend. And actually there was a very similar situation when the supercomputing centers were established in a number of countries. For example, in Switzerland, they decided to have one in the French-speaking part, another one in the German-speaking part, and a third one in the Italian-speaking part. In France, you have a large supercomputer center in the south of France, in the north of France. The situation is basically the same in the US, where the supercomputer centers are distributed by design. Okay, so for all these reasons, and actually another reason anyway, is that it's not easy because of our requirement to use commodity PCs, which are really they are not these rack-mounted PCs, they are really commodity PCs. So one of the problems is space. Another problem which is related is also the power consumption, but space is a non-negligible issue when you want to build these very large facilities. So solution we came out with is actually a hierarchical structure with CERN as the data source for the real events being in the center, and you have several levels of regional centers. So there will be, for example, centers in the USA, number of centers in Europe. We are also discussing regional centers possibly in Russia or in Pakistan, maybe India. And the next layer is the university, the laboratories where the users are. Okay, so now, of course, in practice, things are not as hierarchical as it looks like. So you have a lot of requirements from universities going directly to not the closest connected regional center, but to other ones depending on how the collaborations are structured. And of course, the challenge is whether this structure will work and whether it will be manageable. So that's where the grid is coming. As explained before, the simplistic view is that you submit your job and the grid will do everything for you. So it will identify. So in grid you have various services, one of which is called grid information services. When the various parts of the grid advertise available resources in terms of computer capacity, storage, the type of software they run, the class of users which they are willing to accommodate, and so on. So the grid is supposed to optimize all this, to organize the migration of the data using various techniques. So you can, it will also depend on policy whether we distribute everything to some centers or whether the data is pulled on demand. One of the main things the grid is doing, which is easy to say, is difficult to deploy, is to deal with authentication of the users, which implies the deployment of these X509 certificates and the associated certificate authorities. And the grid is also supposed to interface in a more or less transparent way with various peculiarities of the computer centers involved, to, of course, monitor progress and supposed to recover from problems, which is probably one of the most difficult things. Okay, so the Datagrid project is, you can see here the main partners, CNRS in France, PPARC, which is the Particle Physics and Astronomy Research Council in the UK, NICEF in the Netherlands, INFN in Italy, and European Space Agency, because this is a multidisciplinary project. Okay, and there are also industry with IBM, company Signo in France, Datagrid in Italy, and quite a number of associated partners all over Europe. The project started on the 1st of January this year. It's a 10 million euro project. It's closely coupled with several similar national initiatives. It's multi-science, Olivier mentioned. Is building on existing technology. In our case, we are going to start from the Globus toolkit, which provides a flexible and open framework for building new functions. And other related projects like Condor and various national grid projects. The emphasis in the case of Datagrid, as the name indicates, is on managing a large amount of data. In other words, providing access to data in a seamless fashion across these interconnected, very large PC farms in the various regional centers. Okay. What the project will deliver is working prototypes. Specifically, the plan is to produce one version of the middleware each year for the 3 years of the project, and that each year there will be a test bed which will use this version of the middleware. An important aspect is collaboration with other European and US projects. Actually, collaboration with the US is very important because they have similar projects also involving CERN. Okay. So, and of course, the project has to be open. We participate to the Global Grid Forum and also in the other forums. Okay. So, challenges, I think already mentioned, data scaling in wide is probably the most difficult ones on reliability, manageability of this type of worldwide computing fabrics, usability. Okay, I think I cover most of this. So scientific applications, we have actually Earth observation with the European Space Agency. We have biology that's done by CNRS in France, and high energy physics, of course. And the aim is to deliver a production style environment. So I will go quickly through some of the problems. So we want to maximize the throughput of this global system. So one of the problem is so we in some similar systems which are more computing oriented. So you want to have large number of processors to solve a particular computing problem, but you don't have much data. It's to some extent much easier. So you try to run your job on as many independent processors as possible. In the case of Datagrid, because of the amount of data, you try to run the jobs where the data is. And of course, initially the data is only at CERN, so it has to be disseminated. But once it is disseminated, you don't expect to, once you have a scheduled job to a particular location, to have to transfer a large amount of data. So one of our problems is that it's not so easy to know which, because it's not so easy to know in advance. So it's not easy for when the job is submitted to specify all the objects, all the files which will be needed at execution time, and that's partly because of the way data will be organized in databases. So extracting collection of data will not be easy. Another problem, of course, is how you split jobs. And related one is how do you run interactive jobs on such an infrastructure when you have large amount of data to be available. Okay. I think data management I already covered. Application monitoring is also one of the key issues because of the very large number of components. Well, another problem, of course, is the performance of the whole system and fail-safe operations. On the local side, there are big issues with management of these big, huge computing fabrics. We are developing a number of tools to assist in automating the monitoring, error recovery, being able to understand the performance, and so on. So in terms of infrastructure, we want to operate production quality trans-European test bed. Because of the large number of participants, we will end up with clusters in about 40 sites. I already mentioned that there will be successive version of this Datagrid middleware. The network infrastructure will be actually, we will start with JIVE. The test bed is expected to start in September of this year, which more or less coincides with the deployment of JIVE. Given that JIVE will deliver much higher speed circuits than we thought 2 years ago, in principle we don't have, especially in the first years, any specific requirements beyond being able to access JIVE at 2.5 gigabits. Okay, and also mentioned that one of the key issues is that in this Datagrid project we don't end up with something which doesn't interoperate with similar projects in the US. So here I mentioned too, Griffin is also involves HEP applications and actually involves 2 LHA experiments. Is funded by the National Science Foundation. PPDG is Particle Physics Datagrid, is also a similar project which predates Griffin, is funded by the US Department of Energy. Okay, so here you have a view of the testbed sites all around Europe up to Dubna and Moscow. Okay, I mentioned the applications. Challenges, it's interesting because we came up with a similar warning. So it's a project which is very large, maybe too large, but there was a desire to be cover many partners in Europe. So collaboration with US and GRID we mentioned. I think the last message is important. There is maybe too much expectation from the GRID. The idea is excellent. The deployment, there are major challenges to be solved, particular with deployment of the authentication infrastructure, but they are also, in our case, because we are moving large amount of data, there are major problem at the network level if we want to operate at multiple gigabit per second. Okay, so it may be that it turns out to be much more complicated than some people expect. Okay, so to conclude, I think the vision, it's actually a dream, is that you have easy, reliable access to very large shared computing facilities worldwide without the user having to know much of the details. And the Datagrid project will provide very large, in terms both of computing capacity, also geographic dispersion, very large working test bed, and certainly we will collect a lot of useful and practical experience which can hopefully be adapted to needs of a wide range of scientific and engineering applications. Okay, that's the... Okay.
So we have time for a few questions, please. The floor is open.
Let me speak for a few seconds in favor of hype. This is not the sort of audience where you need to, where it's fashionable to speak in favor of hype. Most of us are scientists, and many of us are Europeans, and we try and keep our feet very firmly on the ground, and Europeans probably as a group characteristic are reticent about saying too much about what they're doing before it's actually been delivered. But the world we live in as scientists and researchers is changing, and if we can't convince our politicians and our press and our industry that we're doing things relevant for them, then we will get less money and less resources in future. So it is very important to keep our feet on the ground and to understand amongst ourselves what we're doing and try to convey to the public the timescales on which it will happen. But we should not be modest. We are trying to do something very important for distributed computing and for sharing scientific resources sharing computing resources among scientific communities around the world. So let's not be too modest.
Thank you, David. Can I make a comment there? I think the Commission has recognized certainly the importance of grid computing, and as you may know, we will evaluate in the coming days 5 more projects. For the next year, another call for proposals in the grid area is foreseen with quite considerable money available for that. This is just some information. If you have more questions, please. Seems not the case, so thanks again, Olivier, and thanks to all of you for attending the session.